Doesn't exist in this room, right? Only physics. All right, y'all. So logistics. I'll do the most interesting one first. I posted your all's pre-response grades, so that's there. Again, the averages for those are really good. Now I did some. How to put it? The grades are like, there was no curving additional. I didn't lower points, I didn't raise points. But the numbers look different, and I sent out an announcement just now clarifying that. So remember that your all's multiple choice was 80% of the test, and then your free response was 20% of the test. So to make the grades actually match that, what I did is I went through and I scaled the multiple choice to out of 80 points, and then the free response are out of 20 points. So that's how you can see that if you want to see the exact percentage, I'm sure WebCourses can do that for you, or you can just take the number you got, divide by how many points is out of total, and that gives you the percentage. What I also did, so remember I did that survey thing, and my hope was that WebCourses would kind of give the bonus points, but what I ended up doing was taking, if you did the survey, which basically everyone did, so that was interesting. Even a couple people that didn't take the exam still did it, so that was interesting. I took those points and I just added them to your free response. And it works out mathematically. So it does make your free response look a little bit higher than it actually was. You can do the math yourself if you want to see it. Subtract 2, subtract 1.5, whatever it may be. But that is in there now. That is in there. So all of that's in there. So at this point, your all's grade is fairly reflective of your current grade, with one big exception, and that big exception is right now, and until the end of the year, there is no final grade posted. That sounds obvious. Of course, we haven't taken the final. There's no grade posted for that. The reason that matters is your final is worth 20% of your grade, and so right now, I only have the first 50%, clickers, quizzes, discussions, that kind of effort-based, and then there's 30% for the tests. And so right now, a majority of your grade is weighted based on the effort part. You are missing the 20% from the final. So the reason I mention that is it may be helpful. I think WebCourses has a thing where you can kind of fiddle around with grades and stuff like that. Does it let you do stuff with the final, or do I need to put a placeholder assignment? Do you all know? I may just put a placeholder assignment in there just so you all can check it. I think WebCourses generally lets you fiddle around with things, but it would be interesting for you all if you actually want to see where you're at. Something that may be helpful is to take your test 1 grade. Just assume that you'll do that well in the final. Whatever, kind of put that in there, and that'll actually give you a more accurate measure of your current grade. Because right now your tests are not weighted. You don't have all the tests in, so it's not, that testing part of the grade is not getting its full kind of weighting, if that makes any sense. And that's why a lot of grades right now, I have a lot of people, and it's going to sound really weird, and you'll be like, what? I have a lot of people that have over 100% in the class, because that extra credit from the effort-based stuff is kind of carrying more weight than it should at this point. The reality is, though, again, if your grade is above a 90% now, you'll play around with the percentages on the final, play around with the numbers, put that in, kind of see where you're at. But just know that I think a lot of people will be surprised when the final comes along. They're like, oh, my grade dropped so much from the final. That's just because that weighting wasn't there. The extra credit was carrying more weight than it kind of does. All right, so whatever. Math things. And there's nothing I can do on my end to kind of address that. That's something that I'm just kind of raising. And that's probably true of a lot of your classes. So just something to keep in mind. Okay, so last class, we did a recap on circuits. I told you all that basically circuits boil down to, you need to add, like, how do you solve these problems? You combine them all into one resistor. You can only combine them if they're exclusively in parallel or exclusively in series. And so you figure out what's exclusively in series, exclusively in parallel, combine that, and then you kind of keep doing until you get to one. That resistor / capacitor gets the voltage of the battery, and then you work backwards. And we talked about that. So definitely, if that didn't make any, it's a problem sets, all that jazz, make certain you look through those. You're going to be doing it on the quiz. I do want to point this out. This is the discussion question. It's the RC circuits. So if you're stumped on the discussion, one, if you show up, they'll just kind of work through it with you. A reminder, I am not testing you all on RC circuits. So this shows up in the discussion because the discussion questions are the same across all the 2054 classes. But I've kind of decided RC circuits, it's not worth the time and energy for you all to go through. But there is a question in that because lining up with that. To that end, there's the equation for charging, there's the equation for discharging. That's what you end up using. But I will just I'll spend 5 seconds on this. Why are RC circuits meaningful? So when you connect the circuit this way, the capacitor builds up with charge. Remember, a capacitor is like a bucket. So imagine like this battery is like a hose, and we're like filling up this bucket with charge. So we're filling it until it has a whole bunch of charge on it. And then when we flip this thing to the other side, now this is my closed circuit. And the electrons here will then try to get to the other side of the capacitor. So you can think of it like taking that bucket and dumping it and getting all that charge out super quickly. So that's conceptually why RC circuits are useful and meaningful and necessary. Mathematically, though, it's not worth the time and energy for you all. What I just mentioned is honestly what I would care about you all knowing. RC circuits, every single circuit basically has resistors and capacitors. Every single one, you will see both of them in there. And this is one of the reasons. So like a defibrillator, when they charge up a defibrillator, they're doing this. They're charging it up. There's resistance as a capacitor. And then when they touch it to someone's body, they're doing the other side. And they're discharging all that charge through their body super quickly. The other really common example of this is, if y'all ever had those disposable cameras and they have the little like switch that you hit, it goes like, it makes like that and it's, you have to wait till a light turns on. I don't know. This is like, I'm not that old, but at the same time, I'm like, who uses disposable cameras nowadays? I don't know. If you ever have an old disposable camera, they usually, for the flash, you kind of flip this switch, it makes like a high-pitched noise, like, and it's like charging up, and then a light turns on, and when you hit the button, it flashes. You are literally charging a capacitor, and then when you hit the button, it discharges that capacitor, and that's what makes the flashlight really bright. That's what makes the bulb makes the flash really quickly. Whatever. Fun things. Okay. Then we did right-hand rule. We had so we said we introduced magnetic fields. Great. We said they're measured in Teslas. We spent a lot of time on this right-hand rule thing. So we said, great, magnetic fields exist. How do we know they exist? If you have a moving charge, it experiences a force. If you have a moving charge, it experiences a force. If it's in a magnetic field. But it's really weird because this force was perpendicular to the direction that the charge is moving. And so we had to do right-hand rule to figure out that direction. There's no getting around it. And because direction matters. The direction this charge goes, up or down, is a big difference. Whether or not you are traveling up or down is a big deal. Depending on whatever situation you're in. So direction matters a lot in the real world. And so, yeah, we did this. We did some examples. And so we'll do one or two more and then get into kind of the next stage. Oh, actually, the last thing I talked about, I'll spend some time on this. So this is the very last question. We kind of ran through it because it's like 1 minute. So we talked about the Earth. We said the Earth makes a magnetic field. The magnetic field points away from the bottom of the Earth and towards the top of the Earth. So you can see the arrows here. They point away from the bottom and they point towards the top. And the question was, okay, the top of the Earth is obviously the north geographic part. The bottom of the Earth is south. Most of us north, south, that kind of thing. But magnets, permanent magnets, also have a north and a south. So we have a geographic north and we have a magnetic north, and they're opposites. They're opposites. The north magnetic pole of the Earth is on the bottom, and the south magnetic pole is at the top. So geographic north, your compass still points north. Your compass still points north. But when it comes to, it's a little unfortunate because they use the same terminology. North and south traditionally to you all means like towards the top of the Earth, and south means toward the bottom of the Earth. Here we're using north and south as the poles of a magnet. North and south are also used as the poles of a magnet. If y'all have ever played with a magnet, let me just, this is a picture. Yeah, you got the two ends, a red end and like a blue end, generally. One's labeled in, one's labeled south. It's not because it's where it's located. It's the magnetic field lines point out of the north into the south. This is, so out of all the things I said, am I going to test you on the Earth and which end is the north geographic? No. What do I need you to take away from this? What is the thing about a permanent magnet you need to know? You need to know that on a permanent magnet, the magnetic field lines point away from the north and point towards the south. You need to know that for a permanent magnet, these two things, the magnetic field lines point away from the north and towards the south, because we're going to need this later on. This is something we're going to need at some point in the class very soon. And so to that end, this is what's important. We need to know this information. I'm teaching you all for a reason. If you don't know which way the magnetic field lines point later on, we're going to have some challenges when we solve different types of problems. Okay? So they point away from the north and towards the south, which is kind of nice. If you all remember electric fields point away from positive and electric fields point towards negative. So if you just think of north as like the positive end and south as like the negative end, you can kind of use existing knowledge to help remember that. Or you can put it on your note card. Up to y'all. Alright. So, we're going to do a little bit of practice, and this is going to segue us into the next thing. I have a charge moving to the right. Yes, to the right. In a magnetic field that is pointed into the page. We also talked about X is into the page, dot is out of the page because it's like an arrow. An X is like the back of the arrow, so you see the back of the arrow going in. A dot is like it coming out. So my question to you is, which way will that charge move? It will experience a force. So basically, what's the direction of that force? What's the direction of that force? That's what I want y'all, just like we did before. I have a charge moving to the right, so this is just practicing right-hand rule. Charge is moving to the right in a magnetic field that's pointed into the page. What is the direction of the force? And I didn't clarify it here. Let's just make it the easiest case, positive charge. Let's make it the easiest one possible. I'm shooting a proton through a magnetic field. Up, down, left, right. And then you know what? Let's give you all some points for this. Boom. Is it, so which way, and I'm going to reword this. I intentionally had this, we'll get to this wording. Which way will a positive charge moving to the right travel? Nope. Which way will a positive charge experience a force if it is traveling to the right in a uniform magnetic field? Great, we got there. All right, up, down, left, right. Easy. The problem not necessarily easy, but making the problem at least was. All right. Good old right-hand rule practice. Right now, my answers are split about 2/3 correct, 1/3. Which is fine. These problems take practice, and that's okay. Like, clicker questions, I don't really care if people get them right or not. But this is good. These problems just do take practice. So the responses here will just kind of reveal that if you do have the wrong answer, that's fine. This will just be something you have to practice. Thankfully, it's easy to practice. Just you do a bunch of them and eventually have it down. All right, we'll go to 105. Oh, we have so few people. Again, I was mentioning this before everyone showed up. It'll be really interesting to see who's in class when we get near the end of the year. 5, 4, 3, 2, 1. All right. Failed to stop question. Yep, okay. Well, no idea. Wild. Doesn't want me to. All right, we're just going to... Yep, well, okay. Yep, still can't stop the question. It's in progress. Fantastic. All right, this is a new one for me. Through the magic of closing it and reopening it again will help it fixes it. But the answer was up. And while we're waiting for this thing, so we'll explain why. Positive charge, so you use your right hand rule. Fingers to the right, magnetic field into the pit. So remember, you point your fingers in the direction it's moving. You can rotate it. Don't twist your wrist, though, because then your fingers are no longer pointed in the right direction. So you point it to the right, you can rotate it, make your palm point in the direction of the magnetic field, and my thumb points up. So the force is upwards. Okay? Let's see. No idea if that last one went through, so I will open this question again for 20 seconds and see how many people get it. Oh, we'll do... Again, that delay kills it. All right, well, I'll give people 20 seconds to answer, and we'll just see what happens. All right, so you obviously know the right answer. Just answer. This is just to make certain I'm giving people the points for the effort and then all that jazz. Whoa, we got more people. That's crazy. It was 59 last time. Maybe the whole system broke. Wow, everyone got it right. Y'all are so talented. All right, 3, 2, 1. Fantastic. Wow. I mean, I say wow. You're like, oh, of course everyone's got it right, but there's always someone. Okay, so why do I mention this? Okay, so if this thing is experiencing a force upwards, well, what's going to happen is the path of that, the velocity is going to change. If you experience a force upwards, it's literally getting pushed upwards. And a force, if y'all remember Newton's second law, F equals ma. You had so much fun with it back then. You don't need to remember it now, but like if there's a force, there's an acceleration. If there's an acceleration, my velocity is changing. So to that end, what does that cause this thing to do? Well, this velocity, as time goes on, will start to kind of veer upwards, right? If there's a force upwards, the velocity is going to start to veer upwards. So let's just kind of take that to the next level. Let's just take this problem and go to the next step with it. So which way? So we just said, as time goes on, that this charge is going to experience a force upwards. That's going to cause, through the magic of rotating this image, it's going to cause the velocity to veer upwards. Ta-da! So now this is kind of traveling upwards. So this is its new situation. It experienced a force upwards that caused it to go upwards. My question to you is, which way is the force now? Now that it's traveling upwards, because there was a force causing it to change upwards, now which way is the force? The magnetic field is still pointed into the page. Nothing has changed there. The direction the charge is moving does not affect the external magnetic field. That's an important thing. Remember, whatever is affecting something has to be external. For example, your own gravity can't affect yourself. There has to be an external gravitational field. All right, we'll go to 50 seconds on this one. In 5, 4, 3, 2, 1. All right, these are looking pretty good, y'all. What's cool, I just want to point this out because it's interesting. If you just rotate your head sideways, it's the same problem as before. So to that end, if you just rotate your head sideways, you can see that the force is this way because it's the same problem as before. But, let's do the right. Again, this shows consistency because what is up? Up is all relative. But we point our fingers upwards. We then rotate our hand so that the palm is pointing in the direction of magnetic field and my thumb points in the direction of force, which is to the right. And then same thing for those online. Bam, force is upward. Well, okay, my webcam's not even on. Now it's on. I turned it off because Physics 1, they don't need to see my face. Also, it just makes my computer chug more. Anywho, palms up, faces up, this is upward, this is into the page. Boom. So this one's to the left. Let's do it one more time. Because now what's going to happen? So now, okay, there's a force to the left. What's that going to cause it to do? Okay, that's going to make it go this way. So now it's going to the left. To the left. What's going to happen now? And we're going to put all this together. We're building a picture, y'all. There's a reason I'm doing this. We're going to put all these pieces together to get to some final result. This isn't, one, it's good practice, but there's actually a punchline at the end of this whole thing. Now the V looks like a delta, but whatever, does the job. Through the magic of... Can I flip it? Oh, it's fine, it's fine. All right. Let's see, how far do we'll go to 50 seconds. 5, 4, 3, 2, 1. Again, we're getting the idea. Again, if you rotate your head upside down, you get, it's the exact opposite of the first one, but right hand rule, do the things. It experiences a force downwards. What's that going to cause it to do? I'm not going to do one more of these just for the sake of I think we've done enough to kind of get the idea. So what ultimately happens, if you all noticed, I kept rotating it, so this one would cause it to go down. And then if we did it one more time, that would cause it to go left. And look at it go! So what's the end result? Why did we do this? Is if we look at the overall situation here, I have a charge going into a magnetic field. What is the path it would take? This is the original wording I had. What is the path that this charge would take? A circle. And it will just keep going in a circle forever and ever and ever. It'll never make any forward, assuming that the magnetic field is everywhere. Assuming that the magnetic field is everywhere, all over the place. This charge, actually let me make it maybe a little bit smaller so I can put the whole circle there. Assuming this magnetic field is everywhere, if there's no magnetic field, there's no force. And assuming it's a constant magnetic field, so some important assumptions. This thing makes a circle. And that circle, it just stays in that circle forever and ever and ever and ever. It'll just keep spinning in a circle. At no point is it getting faster. At no point is it getting slower. Its velocity also stays the same. And this connects to something interesting. A magnetic field cannot do work. That's a throwback to Physics 1. What that means is it cannot increase the energy. It cannot, a magnetic field does not increase the energy. And there's all sorts of really weird examples of where you think of magnets and them increasing energy, and honestly, those ones I'm not even 100% sure on exactly why that, but a magnetic field does not increase the energy, but it does change the direction. And now, another throwback to Physics 1. Let's see how good your memory is. What is the equation for the force experienced by an object with mass m moving at a velocity v in a circle with radius r? I have not taught this to you all. I'm going to remind you of it. But this is from Physics 1. Again, if you don't remember it, that's okay. I'm going to remind you, but this is me just checking, hey, who remembers the equation for the force experienced by an object moving in a circle? Is it v squared over r, mv squared over r, mvr, or v squared m r squared? Like every equation that I give you all, I do not expect you to have these things memorized. This is one of those that will get put on the formula sheet. So we'll finish this one in 5, 4, 3, 2, 1. All right. And again, it is what it is, like as far as what the answer is. It's mv squared over r. Centripetal force. If something is going in a circle, it's mv squared over r. That force, so this is not a physical force like gravity or electric force, the force through an electric field, or the force through a magnetic field. This is not the force caused by something. This is if something is going in a circle, we can do some math tricks, and it turns out that if you multiply the mass times the velocity squared and divide it by the radius, that will give you the force pointed towards the middle. It's also important to remember that this is pointed towards the middle. If you all remember that whole charge moving, if you kind of drew that circle, it always pointed towards the middle. So, the sum of the forces acting on an object that point towards the center add up to be mv squared over r. That's kind of a throwback from physics 1. If you, all the forces, so like for example, well, in this case it's all magnetic field. Fun fact for you all, if something's going in a circle in this class, the reason it's going to be going in a circle is a magnetic field. We're not going to put in gravity, we're not going to put in other things there. Okay, why do we care? Why do we care? Well, what's cool about this, we just put the equation for the force due to a magnetic field, QVB, set it equal to mv squared over r, and we can do math with that. We can solve for things. The force of something going in a circle, which in this case is the force due to the magnetic field, equals the centripetal force. So QVB equals mv squared over r. And then we can also find the period of, we can use the period to find some things with this. We can do some stuff there. So if we rearrange this equation for v, this is the equation for period. That is the equation for it. And if I solve for v in this last equation, so v equals r QB over m. If I just take that and I plug it in right there, I can find the period of it, or vice versa. Okay, so why does this matter? Okay, great. This is just a bunch of math. What's the point? This is how mass spectrometers work. So one functional application of this, I mentioned to you all, there's these devices called mass spectrometers, which for some of you in the medical field will actually be very important. So if you want to determine what a molecule is, how do you do it? There's so many ways. One of the ways to determine what a molecule is, you ionize it. You give it a set amount of charge. -1, +1, whatever. It doesn't matter what it is. You give it a set amount of charge that you know. You know the Q. You then get it to a certain velocity that you can then kind of figure out what that velocity is. And then you shoot it through a magnetic field that you know the strength of the magnetic field. And based on the radius of curvature, you can determine its mass. Based on how much that thing deviates, based on the circular path it takes, you can figure out the mass of that particle. Which is very useful, because if you know the mass of that particle, if you know the mass of that molecule, that can tell you what the molecule is. Because different molecules have different masses. So that's one application for you all, actually something you may or may not interact with the mass spectrometer. A way to identify molecules. Another application of this that's really cool is proton therapy. So proton therapy is, I don't know how new this is. There is facilities in Florida that have this. They're not super common because they require very specialized equipment. I mean, this thing is massive. This little black smudge here is a person. So this little black smudge is a person, and you can see how much stuff you need. Proton therapy is a really cool mechanism where they literally take protons, they put them in a magnet, they put in a cyclotron. What is a cyclotron? It's literally a magnetic field. There's a magnetic field, and you make it go in a circle. The circular path is efficient space-wise. Otherwise, you would need some really giant thing, like if you want to accelerate something, if you just keep going in a circle, and every time it goes around the circle, they can bump up its velocity a little bit. So it kind of starts here in the middle, and it's going, and they have a magnetic field to keep it in that circle, and then they do stuff, they put a voltage to accelerate it. So at some spot, they have a voltage that accelerates it, and it makes a slightly bigger circle, and then a slightly bigger circle, and a slightly bigger circle. Eventually, it shoots out of this thing. It goes along this path, gets deflected. How do you deflect it? Magnetic fields. Magnetic fields are how you can deflect these particles and make them change direction. And you launch them into a person. And you may be like, why am I launching protons into a person? This is to treat cancer. So you put someone, you kind of lock them down so that they're not moving because you want to make sure the protons go where you want them to. These are very high energy protons. When these protons go into the body, what's really interesting, so traditional kind of radiation therapy, say you have someone's arm. If I blast them with a bunch of radiation, the part that's affected the most is the surface. And then it kind of gets weaker and weaker and tapers down. And traditionally, the tumors you want to treat are not on the surface. Well, it depends. I mean, could be. But if they're inside the body, you're actually not getting the highest dosage where it is. So what do they do in radiation therapy? They kind of rotate the person and they expose kind of all the parts of their arm. So if we imagine this is their arm cross-sectionally, you blast them with some radiation here, some radiation here, some radiation here, some radiation here, and you can see they all kind of, wherever they overlap, that's where the highest concentration is. And so that's what would get that. But you still get right into the problem that I've literally radiated like all these other parts of their body. And the point of the radiation is to kill cells. So you damage parts of the body. What's cool about proton therapy is this particle. So you're literally launching a proton into someone. When this proton goes, so it goes through their skin, that's fine. It releases most of its energy when it comes to a stop. So when it stops is when it releases the most energy, and through some fancy physics and math, you can get this thing going at just the right speed so that it stops exactly where you want it to. And so instead of the maximum dosage being at the surface, it instead does kind of the opposite. The maximum dosage is instead kind of at the spot you care about, where it stops. So it's just kind of cool connection to this. Magnetic fields are used to guide these particles, though, to keep them in these circles, and then to redirect them where you want them to. So that is a very practical application of deviating these particles. Anyway, fun connection. You don't need to know anything about what I just told you. All right. So, what do we need to know from all these things? Magnetic fields cause a force in a moving charge. This force is perpendicular to the direction. F equals QVB. We use the right-hand rule to find it. A charge which moves perpendicular to a magnetic field travels in a circle. You can expect to have to do problems with that. Find the radius, find the velocity, so on and so forth. And then I will add permanent magnets. Magnetic field lines point away from north. Magnetic field lines point towards the south. Cool. All right. So that kind of covers the first chunk of this. And now we'll do some problems on it, and then we'll get into the second chunk. And again, I'll upload all this stuff. So, because I'm always so scared of all these things getting, the ghosts ruining things. And yeah, thankfully these problems, the good news is at this point, these are vectors, but no vector addition has happened at this point. Okay, so let's look at one of those circular motion problems. So I have an oxygen 16 ion with a mass of 2.66 times 10 to the minus 26, travels at 5 times 10 to the 6 meters per second, perpendicular to a 1.2 Tesla magnetic field. That's a really strong magnetic field, which makes it move in a circular arc with 0.231 meters What's the positive charge in the ion, and what is the ratio of this charge to the charge of an electron? All right, lots of words. Maybe like, how do I even begin this? The classic, y'all. Spend a few seconds, try to find the givens. And when I say givens, what variable, there's obviously a bunch of numbers here. The key part is here, what variable do each of these numbers go with? And there's actually one number we don't care about at all in this problem. So we see a mass of 2.66. So that's m to the minus 26 kilograms. Cool. The next one, we have a velocity of 5.0 times 10 to the 6. And when it comes to identifying what the units are, like what variable to go with, it's just the unit. Meters per second is always velocity. Kilograms is always mass. Tesla is always magnetic field. Now the last one gets, meters, there is so many different variables for meters. There's D for distance, X for like in the horizontal, Y, R. And so distance is the only one that's got like a whole alphabet of letters you can choose from. So you kind of look around it and you have to decide the right one. Radius, a radius of 0.231 meters. So distance, even though it's one of the simplest conceptual things, has so many different options. X, R, D, is it diameter? So that one you do have to read the words. Okay. We don't care that it's an oxygen 16 ion. Don't need that information. We'll see why as we solve this problem. If we need it, we can always come back and try to figure out what it's used for. All right, what are we solving for? Give you all a few seconds. What variable are we solving for? When it comes to the multiple choice, y'all, this problem-solving process will get you through most of the problems. Because most of the problems I give you all on the multiple choice are one-step or at most two-step problems. Which traditionally means write down your givens, write down your missing, find the equation that relates them, plug and chug. A lot of them boil down to that. Not all, but a good amount of them. All right, we're solving for Q. So what equation are we going to use for this? This is where you kind of hunt through and find the equation. Either if you're like, I have no idea, literally try to find an equation that has the givens and the missing. Or the other way, if you ever see in a circular, something going in a circle, there's only one equation that we're talking about in this class that has to do with circular motion. It's the one I just taught you. It's that mv squared over r, or it really doesn't matter. qvb equals mv squared over r. The order does not matter. mv squared over r equals qvb. qvb equals mv squared over r. So if something's going in a circle, this is the equation you're using. Like that. That's it. Make our life a little bit easier. One of the v's will cancel on both sides. We are solving for Q. Traditionally, I plug in the numbers and then do the math, but because the algebra here is actually not too bad, if I want to get Q by itself, so it's going to be mv over br. All I did is I divided the b to the other side to get Q by itself. That's all I just did right now. You could put the numbers and then you end up doing the exact same thing, but to save myself just a wee little bit of time, I did that. So Q equals 2.66 e to the minus 26 times 5 e to the 6 all over 1.2 times 0.231. And again, what we are doing right now, well, this is kind of backwards. This is kind of what a mass spectrometer does, except instead of finding charge, it finds mass. All right, so 2.66 e to the minus 26 times 5e6 divided by 1.2 times 0.231, And I double check that I plugged all the things in correctly because I've done that. I made that mistake too many times. All right. And if we round this, we get 4.8 times 10 to the minus 19 coulombs. I did a little bit of rounding, and that was a bit purposeful. Because we've only done part A. The next problem says, what is the ratio of this charge to the charge of an electron? This is a good reminder to you all that literally any time you have excess charge, positive or negative, regardless of whether you're positive or negative, it has to be a multiple of 1.6 times 10 to the minus 19. It has to be a multiple of the fundamental unit of charge. You cannot have half the charge of an electron. You can't have 2.5 times the charge of an electron. Because where'd that 0.5 come from? Literally the fundamental unit, the smallest amount of charge you can have is 1.6. So how many 1.6s times 10 to the minus 19? So basically, how many extra electrons or extra protons? So for part B, I just take this answer and I divide it by the charge of an electron, which is 1.6 times 10 to the minus 19. And this one I will do in my head. It's 3. 3. That means I either have, now this problem does not tell you whether I have 3 extra electrons or 3 extra protons. For you to actually figure out which it would be, you would have to determine which way this charge is moving. Which way is it deviating? Is it going in a circle upwards or downwards? Counterclockwise or clockwise? The math here does not tell you whether you have a positive or negative charge. The direction that the thing would end up getting deflected would. But I didn't ask you to find the direction, and I also didn't ask you to find that. So anyway, there you go. I have 3 extra something. It's a nice, straightforward problem. Yeah, we can do this one. This is a good one. It's in the problem set, but I also like this one. A 3 millicoulomb charge with a mass of 3 micrograms is moving to the right with a velocity of 3 meters per second in a magnetic field that's pointed into the page. How strong must the magnetic field be so that the force of the magnetic field and the force of the gravitational field cancel? Okay. Again, these problems have a kind of a lot of wording to them, and always the classic is how do you begin these problems? This one we're going to draw a picture. Anytime you see like multiple forces going on, we should draw a picture, and we're going to see why as we draw this picture. So I have a positive charge, and it says it's moving to the right in a magnetic field that's pointed into the page. What I want you all to do is, what's the direction of the force? What is the direction of the force due to a magnetic field in this picture? This should look familiar because it was actually the first clicker question we did today. The force due to a magnetic field is upwards. Okay? So this particle is going to want to go upwards. So then thinking through the problem, it says how strong must the magnetic field be so that the force of the magnetic field and the force of gravity cancel? I mentioned gravity, so we also have gravity affecting it. Gravity, which way is that one going? Down. And we have just drawn ourselves a free body diagram. Yep, throwback to you all. So this picture is going to help us as we kind of think through this problem and how to solve it. But that's what the picture does for us. The picture helps us to kind of think, what's going on in this problem? How do I even begin this thing? So we're going to write down our givens. Q is 3 millicoulombs, which is 3 times 10 to the minus 3 coulombs. We have a mass of 3 micrograms. Now this is a really fun one to convert. This is 3e to the minus 6 grams, but that's not my base unit. This is one of those, remember mass is funky. Mass, it would be great if grams is the base unit. It's not. It's kilograms. So you actually have to convert this to kilograms, which is going to be 3e to the minus 9 kilograms. Okay? It's a really subtle thing, and this is one of those that would probably catch a lot of people. Grams is not the base unit for mass, and for us to use these numbers in the equations, they have to be in kilograms. Every single equation that ever has mass in it that you all ever calculate, you got to have it in kilograms. All right. What else do we have? We have velocity. That's a nice number. 3 ms. No conversion needed. And that's it. That's all we got for now. Maybe we'll add something later. Step 2. What are we solving for? B, the magnetic field. In step 3, what equation are we going to use? I want you all to spend some time, given the givens, given the missing, given the picture, how would you approach this problem? I will tell you there's no equation on the formula sheet that will solve this for you. So you have to think, what's going on here? How am I going to set this up? Give you all some time to think about it. And the key here is the picture. The picture we draw to help us figure out how to solve these problems. That's why we put it there. So the problem says we're finding B, but given a very specific circumstance. What is the value of the magnetic field so that the force of the magnetic field cancels the force of the gravitational field? So that wording actually tells you how to set this up. I need the force of the magnetic field and the force due to gravity to cancel. The wording there, and we can see that in our picture, we can kind of see that as well, but that's the key wording there. What is the B such that these forces cancel and my thing goes in a straight line? If there's zero force, there's zero acceleration. And then we can kind of put in our pieces. What's FB? The force due to the magnetic field is QVB, sine theta. The angle between, you know what, I'm actually going to put the whole thing, I will put the whole thing here, and we'll talk about what theta is in this picture. And FG is M times G. So this is where I said, is there more givens? Technically, there is a given. G equals 9.8. That's one of those numbers that, it's like the mitochondria is the powerhouse of the cell for physics. Remembering that G is 9.8. Just one of those people tend to hopefully remember it. If not, it's a good one to have in your pocket somewhere. Okay, we'll transfer all this stuff. I don't need the words anymore. We got everything we need. At this point, y'all, the problem is steps 1, 2, 3 are the hard parts. Steps 1, 2, 3 are the hard parts. Everything after that is just plugging and chugging. Now, I will point out here that theta is the angle between V and B, which in this case is not 90. They're exactly perpendicular to each other. So let's go ahead and just kind of take this and expand it a bit. So I got QVB minus MG equals 0. This equation is nowhere on the formula sheet. We had to build this. Free body diagram, all that good stuff. Sure, let's put in the numbers. I'll do it the traditional way I've been doing it with you all. So 3e to the minus 3 times B minus the mass, which is at 3 times 10 to the minus 9 times 9.8. Simplify what we can before we start moving things around. Wow, this one I can do in my head. 9e to the minus 3 times B minus, the other side I'm not going to try to do in my head, minus 2.94 e to the minus 8 equals 0. Add that thing over, divide it by 93. Let's put some parentheses to make that more clear. So b equals 2.94 e to the minus 8 divided by 9 e to the minus 3 equals a number. .27 times 10 to the minus 6. And this is a reasonable magnetic field. It's not, remember, 1 Tesla is huge. 1 Tesla is a lot. You would have a hard time fighting against like 1 Tesla's worth of, if you're holding a piece of metal. MRIs, you know, somewhere around 10-ish Teslas, maybe 7. Okay. There you go. Fairly straightforward. But a good one. It's a good problem. It's got a couple steps in it. Yeah.
If the force isn't moving up, does that like change how we would like set up the problem? Or, like,
Yeah, if the force was, for maybe example, an angle. Yeah, if it was at an angle, then we'd have to find like the component of it that was vertical. But I won't be that deep. Yeah. Yeah. If it was at an angle with it, we would have to find the component of it that lined up with gravity, so those two didn't cancel. Yeah. And yeah, the whole goal with this problem was basically so that this charge just kept zooming along, didn't deviate up or down. Gravity pulls it down, magnetic field wants to push it up, it doesn't want to do either. Okay. So, on to the next thing. The next kind of concept. Do I want to ask this one? Sure. I'm going to go ahead and grab that equation for you all, because you may not have it written down. What happens to the radius in the oxygen problem if I double the strength of the magnetic field? This is just kind of a good ratio one. So here was my original equation. QVB equals mv squared over r. Boom, boom. Everything stays the same. Everything stays the same except the magnetic field doubles. And the question is, what happens to the radius? What happens to the radius if I double the magnetic field? Again, I love asking these kind of problems. If I change this, what happens to this? You can guarantee there will be a few. There was some of those in the last test. There'll be some of those on this test. And I'll show you how to solve these. You can solve every single one of these problems using the same strategy. In fact, I'll tell you the strategy. The first step y'all should do, get R by itself. Get R by itself. On top by itself. So R equals, get R equals, do the algebra to rearrange everything. Get it in terms of everything else. And then just see what happens if I double the magnetic field. What's going to happen to it? Is the magnetic field on the top or on the bottom? Is the magnetic field getting squared or not squared? So rearranging this, if you all rearrange this correctly, you're going to get that R equals mv over QB. It's a good kind of algebra. R gets kicked over QB. All right, and I'll kind of put there. What happens if I double B? This is how you solve every single one of these types of problems. If I change this, what happens to the other thing? Get it in terms of the variable that you want to figure out how it's being changed. The one that you're like, what happens to this? Get that equals all the other crap. And then just whatever changes, change it. All right, we'll go to 205. And 5, 4, 3, 2, 1. And you all can see here, so this is my original. So what happens to it if B halves? We just put a 2 in, or sorry, B doubles. And then you just pull out the 2 to the front. It's on the bottom. Oh, it's halved. This is how you do every single one of these problems I ever give you. Get it in terms of the thing. Whatever the variable is, I say, what happens to this? Get it in terms of that. Change what needs to be changed. Pull it up, pull out the constants. And that's it. And the reason for this, which is kind of interesting, so if I double the magnetic field, it actually makes a tighter circle. If I make the magnetic field less, I get a bigger circle. Because the force is twice as strong, it makes a tighter circle. Okay. So now what we're going to do, and let me just kind of see, yeah. We just have one last little thing, and the good news is, what I'm about to teach you is just, again, it's a classic, y'all. We've been doing, it's the same thing. We start with one thing. What's the electric field due to one moving charge? What's the force if I have 2 charges? And then what do we do after that? We take a whole bunch of them. So instead of what if instead of having one moving charge, I have a bunch of moving charges? And we have a word for a bunch of moving charges. It's current. All current is a bunch of moving charges. And we define current as a bunch of positive moving charges. So, if a single moving charge experiences a force, then a whole bunch of moving positive charges also experience a force, i.e. current. If you have a current carrying wire and you put a magnetic field and they're perpendicular, it experiences a force. For the exact same logic. If one positive charge experiences a force, let's just do that example. I have a positive charge. This is the one that we started the class with. If a positive charge experiences a force upwards due to a magnetic field, literally a current carrying wire is just a ton of, again, current's not actually the way it's going, but we imagine that current is a bunch of positive charges moving to the right. So if I put this in a magnetic field, a current carrying wire experiences a force in the exact same direction that a positive charge does. If the current is going to the right and a magnetic field that's into the page, it's the exact same thing as a single positive charge as far as the direction is concerned. All right. So again, it's just saying current is a bunch of positive moving charges. And if you were okay with positive charges experience a force due to a magnetic field, current is a bunch of charges moving. They will experience a force due to a magnetic field. Current is just a bunch of moving positive charges. Even though it's not really what's happening, that's how it's defined. Okay? All right, this is going to look weird. This is what you all need to care about. F equals I L B sine theta. This part here in the middle, this cross product, don't worry about it. I introduce it as a cross product for you all, but again, that requires kind of calculus. You don't need to know calculus. So in fact, I am just going to scribble over that so you don't even need to worry about it. F equals I, current in the wire. L, how long the wire is. B, the magnetic field, and theta is the angle between B and L. It's the angle between the direction of current and the magnetic field. L is defined as the direction that the current is flowing. So in fact, even though this kind of isn't true, I'm going to change it, and I hate that I in Calibri looks like an L. So I choose, little aside that has nothing to do with anything. I choose Calibri because it's one of the more accessible fonts to read. The lines are straight, there's no other things. But unfortunately, when it comes to I's, it sucks. I hate it. Because an I looks like a lowercase l. So I kind of have to do Times New Roman. Because they actually other ones do it too. There we go. I and B. Let's do it that way. It's literally the same idea as QVB sine theta. This equation is just like this one. QVB sine theta. The I and the L are kind of like the Q and the V. I, how much current do I have? L is also kind of how much current do I have. If the wire is really long, that's a lot of charges in it. There's a lot more cars on a 1 mile stretch of road than there is on a 10 meter stretch of road. There's a lot more charges moving in a 10 meter long wire than there is in a 1 meter long wire. So the length of the wire matters because that's just literally how much charges are in it. I kind of is like how many / how fast they're going. You don't need to understand where this equation comes from, but if you all were okay with QVB sine theta, this is just like that. Just a couple different variables, but it's the same exact idea. The same exact idea. Q and V are kind of like I and L. That's just what I wanted to point out here. Kind of same idea. Okay, we get to use the same right-hand rule. Point your fingers in the direction of current, put your palm in the direction of magnetic field, your thumb gives you the direction of the force. Same thing. So like if we look at this problem here, what's the direction of the force? Put your fingers in the direction of current, put your palm kind of in the direction of B, so I need to keep that way. So this is good because my palm is kind of pointed in the direction of B. I can swing my fingers so they point that way. You can't see my thumb, but my thumb is pointed out of the board. I mean, you can see my thumb, but the thumb is pointed. The force in this specific problem is out of the board. The force is that way. We'll do practice with this. But literally, every problem we've been doing so far with a positive charge moving, just replace that with a current carrying wire, and it's the same thing. It's the same exact thing. Okay? So here's an example of that. I have a current carrying wire pointed out of the page. I have a magnetic field pointed to the left. What is the direction of the force? Do the exact same thing I've been teaching you, except instead of your fingers in the direction of a positive charge moving, fingers in the direction of current. Because current is positive charge moving. That's how it's defined. So, in this case, what's the direction of current? Current is out of the page. My positive charges are moving out of the page. Yeah, so try it out. See how it goes. But anytime you see, it's literally just positive charges. That's what current is. Positive charges moving. The good news is the different answers I'm getting are just based on whether your fingers are pointed into the page or out. Just make certain your hand is pointed out of the page. Make certain your fingers are pointed out of it. The people I'm seeing that are getting the wrong answer, you have the exact opposite of the right answer. So that's good. Like that's in the right direction. All right, we'll close this at 35. In 5, 4, 3, 2, 1. All right, so same rule, y'all. Current is just positive charge moving. So you take your fingers, you point them out of the page. You make it so that your fingers can swing in the direction of B. Oh, they can't do it, so I should rotate my hand. Oh, now they can. My palm kind of points in that direction, and my thumb is pointed down. So hand goes out of the page, you rotate your hand, thumb is pointed down. And again, the answers here, most of that, 2/3 that, 1/3 pointed up. But hey, that just means that you probably, if you put the up, either you were using your left hand, so be very careful. It sounds stupid, just like right hand rule, make certain you use your right hand. Sounds obvious, but when you're in the middle of a test, you may just like, oh, I get my hand. If you are right-handed, it is very likely that you'll be writing with a pencil in your right hand. At which point, you will just use the hand that is free, which is your left hand, and you will get the wrong answer. So that is something to be careful of. In the middle of a test you made, like it sounds like a right hand rule. Of course this is my right hand, but you may just be like, oh, my pencil's held in this hand. I'll just use this one, and you'll forget that it gives you the wrong answer. If I use my left hand, I get a force that is upwards, which is the exact opposite of what it should be. So that's one way, or if you accidentally pointed your fingers the wrong way. Out of the page is out of the page. All right, cool. Okay, so what is the force per meter on a lightning bolt at the equator that carries 20,000 amps perpendicular to Earth's 3 times 10 to the minus 5 Tesla field? What is the direction of the force if the current is straight up and Earth's field direction is due north parallel to the ground? All right. So we got a lightning bolt. It's good to draw a picture. Here's my lightning bolt. Whatever. We'll imagine that it's a straight wire. Now, something interesting about lightning bolts. I told you in this case the direction of current is up. So the direction of current when it comes to a lightning bolt is up. And you may be like, that's weird. I thought lightning bolts go like top to bottom. And they do. Because current is not what's actually happening. Remember, current is not what's actually happening. Current is the opposite of what's actually happening. The reality is negative charges are moving downwards. Current is defined as the direction of positive charge, which is not the reality. Okay? So just good to clarify that. Let's just say that into the page is due north, because otherwise I have no idea how I'm going to draw that. So that's the magnetic field. We'll put north. That's into the page. North. Okay. Fantastic. All right, let's write down our givens. We have a 20,000 amp current. We have a magnetic field that is 3 times 10 to the minus 5 Tesla. That is the strength of the Earth's magnetic field. We are solving for, and this is something that's going to be funky, we are not solving for force. We are solving for force per meter. And why is that important? And that's why I'm actually chose this problem in particular. Force per meter is going to be force per length. Length is in meters, force is force. We're not solving for force. We are solving for the force per meter. This actually makes your life easier, as weird as that sounds. And we're going to see why we have to do this. If you try to solve for force, you'll immediately see that it's impossible in this problem. So let's look at the equation to see why this is impossible. So why this would be impossible if you were just solving for force. So force equals ILB sine of theta. Now in this problem it said they're perpendicular, so that's 90 degrees, so that's going to go away. That'll be sine of 90 is 1. If you look at this equation, if we were just solving for F, we would need I, L, and B. We would need to know the current, the length of the lightning bolt, and the magnetic field. Nowhere in the problem does it tell you how big the lightning bolt is. So to that end, just rearrange this equation. Divide the L over to the other side, and that is the force per length. The force per meter. Force per meter is honestly probably a more useful measurement. Because then if you have a really long wire, you get more force, you can kind of carry that forward. But expect to see that on these problems. Expect to see this pretty commonly when you are solving these, where I don't say what's the force in the wire, I say what's the force per meter. Force per length is also another way of wording that. And then at this point, y'all, it's basically super easy. Just multiply two numbers. 20,000 times 3e to the minus 5. And what's cool about this problem is this is real. Like, this is actual real numbers. This actually happens. Doesn't change too much. Lightning moves so quick that who cares how big the force is, it doesn't affect it that much. But you do get 0.6 newtons, which is kind of cool. 0.6 newtons per length. It's not very much, and it's over such a short period of time. And my units here, I almost fudged that. Newtons per meter. Force per length. Newtons is force. Meters is length. Okay, and I'm going to let you all try to find the port. This is a good practice. The more right-hand rule practice you get, the better. So now go ahead, see if you can figure out what the direction is. There's no math to this. It's right-hand rule. And I'll tell you, whatever answer you get, try to give it in north, south, east, or west. To give you a frame of reference, y'all, I'll put this down for you. If north is that way, west is this way, east is this way, south would be out of the board. So, which way is the force going to be? The force will always be perpendicular to the direction of current. That's why it's not even an option of up and down. Up and down is not an option. Okay, so, and I told you the current was straight up. Didn't need you to know that lightning charges are actually moving down. Current's the opposite way. I gave that to you. So yeah, your hand goes up. Fingers point up. You put your palm in the direction of the magnetic field due to the earth, which is into the page, and you get to the left, which in the way that we drew our picture is west. So part B, the answer is west. Which is my name. How fun. Yeah.
How did you know that
Yeah, west is
field was into the page?
So I chose that.
Oh.
I chose that. I could have chosen anyway. It just said north, and I decided to make north into the page. Let's actually look at this problem from another perspective, because I think it is good. Let's instead look at this problem from above. Above is kind of easier. So if we draw north, south, east, west. So north, south, east, west. So we have a magnetic field that's going north. That's our B. If you're looking at it from above, which way would current be? That's my question to you all. Which way should I draw current? According to this problem, current is pointed up. But if you're looking at this lightning bolt from above, from the clouds, which way would that current be? This is some spatial reasoning, basically. Which way would the current be if I look at this thing from above? If you said out of the page, that's the direction of current. Again, you have to think about it. I am looking from above at the lightning. The lightning, if I'm looking at it from above, lightning's traveling towards me. Because I'm above it, and it's traveling up, and I'm above it, and up is above it. And then if we process the same thing, right-hand rule, fingers point out of the page, magnetic field's up, my thumb points west. You get the same exact answer. If we didn't, then I drew the picture wrong. Thank goodness I did. So this problem just requires some spatial reasoning. Good thing to kind of practice through. Spatial reasoning is an important skill in physics. Okay. Doing a couple more practice, and we'll kind of run through these, and then that's basically it. The next ones are just practicing finding the direction of force in a current carrying wire. Okay. So, what are the directions of the force for each branch of the square loop shown below? Let's just go ahead and pick one spot at a time. So I have a loop here of wire. So the current is going in a counterclockwise loop. I have a magnetic field pointing to the right. And my question to you is, what is the direction of force on the bottom of the loop? Just this part here on the bottom. Just the part here on the bottom. What is the direction of the force? Is it into the page? Is it down? Is there no force at all? And therefore no direction? Or is it left? So maybe I should reword this one to no force. What is the direction? So is there a direction, and if so, which way is it? Or is there no force whatsoever? We'll go to 120. All right, and 5, 4, 3, 2, 1. All right. So, all right, point your fingers, right hand. Point your fingers in the direction of the current. Point your palm in the direction of the magnetic field. I can't. There's no way for me to swing my fingers in the direction of B. They're already pointed in the direction of B. So this is a good reminder to you all of the equation. You always kind of have to keep this somewhere in the back of your mind. So force equals ILB sine of theta. What's theta is the angle between I and B. In this problem, theta equals 0. Sine of 0 equals, and sine of 0 equals 0. So the force is 0. It's the same rule as before. When you had a positive charge moving, same thing. If they're parallel or anti-parallel, there is no force. If you are moving the same direction of B or opposite the direction of B, there is no force. You get the maximum force when you're perpendicular. You get no force when you're parallel or anti-parallel. Very important rule to remember. When you are parallel or anti-parallel, there's no force. And when you're doing right-hand rule, if you're doing right-hand rule and you're like, I have no idea how to get my palm in the right direction, that's probably because there isn't a force. Because you can't do it. The right-hand rule doesn't work. You can't. At no point in the right-hand rule did we say you take your palm and do that. No. All right. What's the direction of the force on the right side of the wire? This one should hopefully make you feel better. First check, is it parallel or anti-parallel? It's not. So you don't have to worry about the same snafu as last time. In this case, they are perpendicular to each other. The current is going up, which if we kind of put the magnetic field over here, that is perpendicular to it. So the magnetic field is perpendicular, so we're fine. We're not breaking, it's not 0. All right, we'll go to 55, and I want to make sure I have one more minute to get to the punchline of this whole thing. There's a very specific reason I'm asking you to do a loop. All right, so 5, 4, 3, 2, 1. All right, so current is up, magnetic field's to the right. I get a force into the page. So I get a force into the page here. Good one to practice. So this is into the page. If you do the other side, you get the exact opposite force out of the page. This one has 0 force. This one has 0 force. If I have a loop, and this side's getting pushed into the page, and this side's getting pushed out of the page, now I'm double checking myself. Yeah. What's this thing going to do?
Your palm's away from B.
So the
Whitby?
huh?
You go Whitby?
Whitby. Yeah. So what's going to happen here? Take this loop. One side's getting pushed in, one side's getting pushed out. What's that going to cause the loop to do? Spin. You've just invented electric motors. This is how electric motors work, y'all. You make current go in a loop. At halfway through the rotation, current's going one way to cause it to rotate one way. Then when it gets to that point, you flip the current, and that actually then causes it to keep going and keep going and keep going. To that's how electric motors work. All right, I'll talk about it more next time. That's my time. But it's a cool punchline at the end. This is how electric motors work. That's why this stuff's so useful, important. Those electric skateboards you see, this is how they work. Electric cars, this is how they work. Your hand mixer, this is how it works. Literally anything that takes electricity and makes motion, there's a magnet and a current carrying wire in it, and a loop.
Yeah, it's not like Whitby on the cage. Yeah, oh, yeah.